to the next topic. Let's talk about applications and higher layer connectivity. Again, we have a very good contribution by Ethernovia. Brian Petersen entered the networking field at 3Com back in the time when 10 megabit coax was very state of the art. Probably you have some memories on that. Brian's career has included major system companies like Cisco, Juniper Networks, Silicon companies, Cheer Systems, Broadcom, and startups like Grand Junction Networks, Greenfield Networks, TerraBlaze. In 2018, he joined Ethernovia as a distinguished engineer and is focusing on the development of revolutionary Ethernet silicon for the automotive market. I'm curious to see his presentation. Welcome to the stage.
Thank you. Serialization is a fundamental component of computing. In a nutshell, serialization is the process of converting structured data to a byte string and later restoring that structured data from the byte string. When I use the term structured data, what I'm referring to is a C-style struct that may contain a collection of individual scalar variables, enumerations, arrays, and nested structs. The serialization of structured data is essential for data storage and for data communication. Basically, anytime you want to move structured data through time or space, you need serialization. To be useful, serialization should have some important attributes. These include the preservation of semantics. For example, the names of the variables, their types, and their hierarchical relationships must be preserved. Serialization should also provide architectural independence. A little endian system must be able to exchange data with a big endian system. Various programming languages have their own preferred methods of organizing variables within the allocated memory. A program written in C++ must be able to exchange data with a program written in Python. Message evolution allows the definition of structs to change over time. Variables may be added and variables may be removed. Type safety ensures that, for example, a 64-bit integer is not accidentally interpreted as a double precision floating point number. And of course, the serializing algorithm should provide efficient setters and getters and minimize the number of bytes on the wire. One of the primary applications for serialization is remote procedure calls. A remote procedure call, like any normal function, can accept input parameters and return result parameters. In this example, A and B may be something simple like 8-bit integers, or they may be complex structs. A target of an RPC may be local or remote. For a local RPC, the parameters may be passed back and forth using pointers. Remote RPCs require serialization to pass structured data. Ideally, an application is unaware of the locality of the functions that it's calling, and it operates the same regardless. It is not unreasonable to apply serialization of structured data for local RPCs. To serialize data, a sending application must store or update variables in memory using setter methods. The serializer then examines the structured data in memory and generates the serialized byte string. The deserializer interprets the byte string and stores the variables in the receiving memory, thus restoring the structured data. At this point, the receiving application is notified and may access individual variables using getter methods. Now, I'm going to return to this drawing a few times to point out where various kinds of processing is required and the impacts that processing has on the CPU performance and network utilization. There are several broad categories of serialization. These include human readable, memory copy, and TLV. In human readable serialization, as its name implies, is human readable text that is either fully or mostly self-describing. Like for example, the variables or individual variables are expressed using key value pairs. The name of a variable is accompanied by its value. The setters and getters in human readable serialization, are reasonably fast and performant. However, converting numerical values to text and assembling long byte strings requires a lot of CPU time. And that's shown in this drawing by the relatively narrow setters and getters blocks and the fatter serialization blocks. Another issue with human readable serialization is the data expansion that occurs on the wire. In this example, a number that could easily fit within a single byte requires 15 bytes on the wire. And this pretty much disqualifies human readable serialization for any performance-sensitive application. Examples of human readable are JSON and XML. Next up is memory copy. In this one, the serializer and deserializer functions have been reduced to the point where they do almost nothing at all. But the way it works is that the structured data resides in a block of memory, and that memory is copied to the payloads of one or more Ethernet packets, and then those are then deposited in the receiver, and you've automatically restored the structured data simply by copying memory from one system to another. Now you can see that the serializer deserializers are extremely tiny in this drawing, but the setters and getters have become quite a bit fatter. And the reason for this is the normalization that must be performed by the setters and getters while minimizing the amount of memory that is consumed. For example, if an array has a highly variable element count, then the normalization requires that memory may require allocations, deallocations, copies, fragmentation, in order to accommodate the changes of the array size while minimizing that array's memory footprint. Another issue with memory copy, as a minor issue, is that numerically small values may be inefficient on the wire. Here, a value that fits in 1 byte may require a 64-bit integer on the wire. Examples of memory copy protocols include SumIP, Cap and Proto, and flat buffers. Now, the proponents of these protocols tout how fast their serialization is, but they tend to be rather quiet about the performance of their setters and getters, the memory consumption, and the efficiency on the wire. So the final category is TLV tag serialization. TLV tag serialization differs from memory copy in that the in-memory format and the on-the-wire formats are different. This means that various forms of data mapping and translations and compression are required for transmission. The general idea behind TLV tag serialization is that each variable on the wire is preceded by a tag that contains a small amount of essential information. First up is a type indicator, which groups together a number of high-level types to a small number of foundation types. The number of foundation types is small enough that this can be expressed in as few as 3 bits. Up next is the variable ID. The variable ID acts as a stand-in for the variable's name. And finally, there's a length field that's required for certain types, such as arrays and embedded structs. The purpose of the length field is to indicate the serialized length of a variable so that a receiving system can skip over a variable that it does not recognize. Examples of these serialization schemes are the TLV variant of SumIP and protocol buffers. Now you notice that setters and getters are fairly narrow, that meaning there's low CPU workload for accessing individual variables. However, the serializer and deserializer blocks have become quite fat. And this has to do with the complications associated with this type of serialization. Now we'll explore why the CPU workload is so high in coming slides. But first I want to talk a little bit about the on-the-wire efficiency. Yes, the serialization tags do take space. Depending on your protocol and other circumstances, it can take anywhere from 1 to 8 bytes to generate a tag. However, despite the size of the tags do offer opportunities for improved efficiency on the wire. For example, the length field that's required for an array means that only an array's valid values and no white space needs to be transmitted, as may be the case with a memory copy protocol. The variable ID values allow for the suppression of optional variables. So if a variable is not set to a value, there's no reason to transmit it. The receiving system will detect this case and will either substitute a reasonable default value or will throw an exception. And finally, protocol buffers in particular supports the compression of integers, reducing the serialized byte string length. Now, to give you something objective to consider, we at Ethernovia put together a serialization performance test using a simple set of nested structs. Now, for those of you who are not familiar with this syntax, this is the dot protofile that we used. The numerical values that are seemingly assigned to the variables are actually the variable ID values that are transmitted on the wire. Now, as you can see, the top-level message struct includes a mid-level message struct as a member, and the mid-level message struct includes the bottom-level message struct as a member. We loaded up these structs with random data such that the resulting serialized byte string was 102 megabytes long. This gave the CPU something substantial to work on and provide us with meaningful data. Using a single core of an AMD EPYC CPU, we're able to serialize at 394 megabits per second and deserialize at 480 megabits per second. The total full duplex rate was 216 megabits per second. Now, bear in mind, the CPU was 100% devoted to the task of serialization, and these numbers do not include any networking protocols or other overhead. Now, to put this performance in perspective, if this CPU had, for example, 6 10 gigabit per second Ethernet links available to it, and the bulk of its communications required serialization, then 100% of that core's effort only yielded 0.36% of the network's total capacity. Now, your mileage may vary depending on your choice of CPU and how many cores you devote to communications. Regardless, I think it's pretty clear why the benefits of fully featured TLV serialization are not taken advantage of in automotive Ethernet, given the cost and power sensitivities of the ECUs. So why is TLV serialization so slow? Well, there's a number of factors that contribute to that. There's the compression and decompression of integers. There's the length determination process that's required during serialization. And there's the mapping of variable IDs to the functions and parameters required to store variables in memory during deserialization. Let's explore each of these in a bit more detail. Protocol buffers has this integer compression technique that effectively strips off leading zeros. These variable length integers are known as variants. The variant process grabs 7 bits at a time, appends a more bytes bit to each byte, and that more bytes bit indicates whether or not more bytes are required. These bytes are then transmitted in little endian byte order such that the last byte of an integer is the first byte whose more bytes bit is set to 0. In this example, a 64-bit integer is reduced down to 3 bytes. For signed integers, whose leftmost bit is set to a 1 for a negative value and would compress very poorly because of it, zigzag encoding is used. The idea behind zigzag encoding is positive and negative values are shuffled together such that the serialized length of an integer is a function of the magnitude of an integer's original value. Now, complex variables such as structs and arrays require a length field. However, the length of a variable is a function of the lengths of that variable's nested variables. So that means you have to explore the hierarchy of the variables in your structs. Variables A through N have these numbers to the left of them that indicate the order in which you have to explore these variables. This is a depth-first exploration of a tree graph. The arrows and curly braces on the far left indicate which variables contribute to the lengths of others. For example, the variable J, its length is a function of the variables K and L. Once J is known, we can determine the length of H, and ultimately we can determine the length of A. All complex variables require this type of examination. And for protocol buffers, which compresses its integers, we have to examine every integer because each integer's serialized length is a function of the value that it holds. Now, one of the bigger problems is that a sending system is not constrained to transmitting the variables in any particular order. This means that we have to examine each individual variable ID and map it to the function and parameters required to store that variable. What makes it tricky, though, is that the variable IDs are context-specific. In this example that we saw before, you'll notice that variable IDs 1, 2, and 3 are used repeatedly. These are all separate and very different variables. ID 1, for example, is used for a string, is used for an array of structs, and for an individual struct. What this means is you cannot directly use an ID value as a pointer to a block of memory or to a block of code. Instead, you have to consider the variable IDs within the context of the family tree. Doing so makes it possible to store multiple instances of the same variable in separate memory locations and to support multiple different variables sharing a common variable ID. So the TLV serialization that I've been talking about is a very important tool for advanced software development technologies. Things like the Kubernetes and the distributed computing that Anil was talking about earlier relies on the rapid transfer of structured data from system to system. Without it, the system won't work. And as I've shown, there's significant performance challenges with this type of communication. So what can be done to accelerate this? Well, one option would be to accelerate the setters and getters and use a memory copy protocol that already has fast serialization. The challenge here is coming up with an acceleration method whose benefits outweigh the penalties. In other words, is the time saved by the accelerator then lost to the time required to transfer the data to and from the accelerator? Another option is to accelerate the serializer and deserializer and to use a TLV tag protocol that already has efficient setters and getters. The challenge here, of course, is the complexities of the serialization algorithms that I've already described. However, despite these complexities, I think this approach holds a lot of promise. The reason I think so is because you'll notice that the serializer and deserializer functions operate on big chunks of data, and they're directly in line with the network connection. This makes it a very attractive target for this kind of work. As automotive networks are called upon to convey an increasing amount of varied traffic, the demand for the transfer of structured data is only going to increase over time. The fully featured serialization that I've described supports architecture independence and type safety and a whole host of other positive attributes. But and is also a very important tool for modern software development, modern software architectures, and software methodologies. But as I pointed out, there's significant performance challenges associated with this. But if we solve these performance issues, I think that future automotive Ethernet networks will benefit tremendously. So I hope I've given you some insights into the promise and pitfalls of TLV serialization and why I'm optimistic for the solution. Thank you very much.
So thank you, Brian. Are there some questions? I think so, yes.
Yes.
Please go ahead.
Thanks for the talk. I'm wondering, have you looked into how basically this rather complex access patterns to the serialized data impact caching behavior or maybe page local behavior in operating systems? Because in a way, if you load that 100 megs and everything gets cached and you have nice access patterns, there should be quite a huge difference in performance when you don't have nice access patterns. Like going to memory is, I don't know, 100 times slower.
Yeah, there are orders of magnitude depending how far away from the CPU registers you get. Every step is like an order of magnitude slower. I don't have a good solution to that off the top of my head. You know, if you could build a system that detects that newly arrived structured data is now in main memory and the caching system detects that and preloads the cache before the processor even asks for it, that could be one method of significantly improving the performance. But I don't have a particular solution in mind.
Okay, thanks.
Of course.
So further questions? Seeing none, then thank you very much, Brian.
Thank you.